In this lecture, let us discuss about electronic transducers for wind tunnel experiments. In this slide, we can see a couple of pictures where you can see a small metallic wing model. You can see that the model has been inserted into the test section of the wind tunnel with a certain servo drive which can change its orientation. And then there are some electronic instrumentation associated with the servo drive, so that we can control it. That means, in wind tunnel experiments, we cannot alone survive on mechanical equipments like what we have studied during the last few lectures, where we discussed about pitot tubes, we discussed about manometers, we discussed about mechanical balance, etc. So, electronic instruments also are a very, very important part of internal testing. And if you look at electronic equipments or instruments which are used for wind tunnel experimentation, you can broadly classify them into three categories, namely transducers, signal conditioners and data acquisition systems. So, over the next few lectures, we will spend time on these individual components which are of very large utility in today's wind tunnel experimental world. For example, when you put some internal models where you have pressure ports, those pressure ports can be connected with tubings to a pressure transducer. It is an electronic gadget which can receive those pressure signals from the different ports of the model and then finally get it converted into some kind of an electrical signal. Similar is the case with sting balance, which has the capability of sensing forces which are acting on a wind tunnel model and converting them into electrical signals. And then those electrical signals are fed into certain data cards, and then they are further ported into the computer, where you have certain softwares which can handle the data, and then you can post process the data using those softwares appropriately, so that you can do the necessary calculations with the data. So, this entire process is schematically shown in a diagram like this, where you have the model here, you have the necessary electronic instrumentation to change its orientation, to obtain pressure, to obtain forces, etc., provide those electrical signals into a signal conditioner, where you can do a number of functionalities. For example, amplifying the signal, changing it to a format where you can further provide it to a PC, where you can save it, you can process the data either real time or offline. Therefore, electronic instrumentation is a very, very important aspect of modern day wind tunnel testing. In this lecture, we will mainly concentrate on electronic transducers, which happen to be one of the elements in the electronic instrumentation. So, as I mentioned earlier, that in last few lectures we were mainly looking at mechanical instruments like manometers, mechanical balance, etc. We need to now realize that why we need to look beyond them. So, there are reasons why we actually need to look beyond the mechanical instrumentation. One is that they lack fast response. That means, they take more time to respond to a certain physical signal and provide you the necessary output, which may become a big impediment if you have very rapidly changing data which is coming from the experiment. So, mechanical instruments will never be able to respond to such rapid changes. Also, measuring intermittent or transient very high or very low values is beyond the capacity of mechanical instruments. Most of such inputs will get filtered automatically due to the damping within such instruments and lack of fast response. Also, the amenability to automation is virtually impossible in mechanical instruments, but which is regularly done for electronic instrumentation. And these are essential ingredients for measurements which involve unsteady flow fields, that means rapidly changing flow fields, which is part and parcel of aerodynamics. Also in aerodynamics, as you know already from your experience on compressible flows, that sometimes you have to look at very short duration measurements. Typically what you see in blow down supersonic wind tunnels, where the blow down time may be short, the initial time you cannot record the data because the flow takes a little time to establish itself. You have a starting shock sweeping through the test section, then the flow stabilizes, and by that time within the next few seconds the tunnel would come to a halt because the high pressure gas is getting consumed. Therefore, you typically have very short run times, and within that you need to acquire a lot of information. Therefore, short duration measurements are best tackled with electronic instrumentation. Extremely short duration tests are involved in shock tubes, where you will get a very minuscule time corridor within which you need to have very high fast response equipments which will respond to rapid changes which occur within a very short period of time and record them without error. Therefore, we now understand that why we need to look beyond mechanical instruments as far as wind tunnel experimentation is concerned. So, most of these above limitations can be overcome. As I said already, that such a electronic measurement system would consist of three vital components: pickup or transducer, signal conditioner, and data acquisition system. In this particular sequence, the information essentially flows. The pickup or transducer, what does it do? It receives the physical quantity, which could be pressure or force or some other physical input. It may be strain, for example, mechanical strain on a particular model, which is being measured. And what does the transducer deliver? It delivers a proportional electrical signal to the signal conditioner. This is the job of the transducer. This is the number one component in the entire chain. What is the number two component going to do? In the signal conditioner, the signal is amplified, filtered. There may be noise in the signal, so you need to filter, and you may be modifying the format of that data so that it becomes acceptable to the next element in the chain, which is the data acquisition system. What is the data acquisition system, by the way? That is the third component. It may have different forms. It may be a meter which records the reading and displays it. It may be an oscilloscope showing the wave pattern. It may be a PC where the data gets stored, saved, and the data can be processed further and displayed. Either it may happen real time, you can see it as it happens, or it happens after the experiment takes place and you have time to do all that. Only thing is that you need to take care that the data is adequately stored. The processing, the displaying can happen later. So, that is the offline approach. When the data is coming out from your pickup or transducer and the signal conditioner assembly, then doing all that as it actually happens at such fast rates may be a tough challenge. That is why very often the storing or saving of the data takes place at that point, and the rest of the functionalities happen later. That is typically what we mean by the offline approach. A transducer is a device which provides an electrical output signal for a physical quantity where auxiliary energy may or may not be required for operating it. Now, we are saying right from the beginning that the transducer has the responsibility of delivering a proportional electrical signal. So, how is it going to produce that electrical signal? For that, you may actually need to give it some kind of auxiliary energy or power to excite its elements, but that is not a necessity. It depends on the kind of transducer that you are handling. For certain transducers, you may not need it at all, but most of them do need an energy feed, a power feed. You may need to supply current with certain specifications to the transducer, so that it is able to send you back the output signal, which is proportional to the physical input, which may be force or pressure or some other physical input. Now, transducers which are used in wind tunnels can be broadly categorized into these following 4 groups. We will spend most time on the first one, which is called as a variable resistance transducer, which is nothing but a resistance strain gauge. It is mostly used in wind tunnel applications because of its unique operational characteristics. Others are variable capacitance, variable reluctance, and piezoelectric transducers. Let us look at what variable resistance transducer is all about. It of course has strain gauge as its heart, and it is going to have variable resistance in terms of its length. As there is a change in length, there is a change in resistance. That is the basic principle. So, the change in resistance will ultimately end up producing some kind of an electrical signal. The strain gauge can exist as a thin wafer like device which can be bonded to a variety of surfaces. Metallic strain gauges are manufactured from small diameter resistance wire such as Constantan, or etched from thin foil sheets like what we see here in that small picture. In terms of size, it is much smaller than what we see in this picture, but you can see the very compact wire mesh kind of setting that you have on that thin foil, stuck to that thin foil, and then this entire assembly is further stuck to a certain surface on which you desire to do the measurement. If you want to measure strain along more than one direction, then you have to have a 2-element or 3-element strain rosette instead of a single strain gauge like what we see in the figure. The resistance of the wire or the metal foil changes with length as the material to which the gauge is attached undergoes tension or compression. So, when this foil is attached to a certain element, let us say a rod, with some portion of it flattened on which you have mounted the strain gauge, and you are subjecting it to some axial tension. By virtue of that, there will be a small change in length of this strain gauge which is fitted to that surface, and that changes its resistance. That change in resistance finally gets converted in terms of an electrical output. In a gauge diaphragm pressure transducer, strain gauges are directly bonded on the diaphragm. So, pressure transducers of the electronic kind often have a diaphragm on which the strain gauges may be stuck. When you subjected it to some differential pressure, then the diaphragm deforms, so does the strain gauge, and therefore, it ends up producing an output voltage. So, you can see a small schematic diagram here. There is a small pressure chamber where you are applying some pressure, and on one side of it you have a diaphragm which undergoes deformation which is proportional to the pressure in some way, and then you have a strain gauge stuck to it, and the strain gauge is given some voltage input as excitation, and it is connected with a certain circuit which we will discuss later, which is called as a Wheatstone bridge circuit. And with the help of that circuit, as we mentioned earlier, there will be an output voltage created when the strain gauge deforms. This is an example where strain gauges have been stuck on the surface of a electronic balance. So, we have earlier seen a schematic diagram of a mechanical balance, where we had used wires on which spring scales were suspended. Here we are talking about using strain gauges to record the deformation of a balance, which deforms because it is connected to some kind of a model which is mounted in the test section, which I am drawing in a much smaller scale just for demonstration. So, you can understand that whatever loads are acting on this model get transmitted to this balance. The balance deforms to a very small extent, but even the smallest of deformations can be captured by these strain gauges, which are extremely sensitive to change in length, and consequently the voltage signal is generated. So, we by now had gone through the basic idea already. Let us do a few calculations whereby we can characterize the strain gauges a little more in detail. So, we are going to talk about sensitivity of a strain gauge, and that is best explained through what is called as a gauge factor. It is defined as the unit change in resistance per unit change in length. This is the definition of gauge factor, which is a very important one. So, you have the gauge resistance, change in gauge resistance, unstressed length and change in length. When you are talking about an axial strain on the strain gauge, then you are talking about delta L by L being represented as sigma. Now, you can imagine that the strain gauge comprises of several loops of a very thin wire, and that wire has a circular cross section with diameter d. The resistance of that wire would then be defined as rho L by A, where rho is specific resistance of the conductor material, L is its length, A is its cross sectional area. Assuming circular cross section in unstressed state, the diameter of the wire is considered as d, and therefore, we have this formula. Now, we are subjecting it to some tension. Consequently, there is a change in length delta L, and there is a consequent decrease in its diameter, because it is elongating. The volume of the wire anyway remains conserved, therefore, the diameter has to reduce. This is the change in resistance. So, there is a change in length, there is a change in diameter, increase in length, corresponding decrease in diameter, and when you take the L out, you get a ratio dl by L here, and when you expand this expression by taking d square out, you can neglect the higher order term, which is basically the square of this, and you get an approximate expression like this. The above equation may be simplified by using the definition of Poisson ratio, which is nothing but ratio of strain in lateral direction to strain in axial direction. So, on elongation, your diameter has shrunk because the wire has extended. So, the delta d by delta L by L, that is going to give you the Poisson ratio. Further, take the expression forward with the introduction of Poisson ratio here, and then you can approximately represent it like this by taking this term to the numerator and replacing the combination rho L by pi by 4 d square part by r, and finally, after further expansion and neglecting higher order terms, you get an expression like that. So, based on this, the gauge factor comes out to be 1 plus 2 mu. So, it can be directly correlated with the Poisson ratio, and it is known that for most metals Poisson ratio varies between 0.25 to 0.5. So, if you substitute that here, the gauge factor varies between 1.5 and 2 for most metals. When you alloy them, then you could get a variation. For strain gauge application, of course, high sensitivity is very desirable, and large gauge factor means a relatively large resistance change for a given loading, which can be more easily measured than a small resistance change. So, having a large gauge factor is always advantageous. Now, in this respect, semiconductor based strain gauges have a much higher gauge factor, almost 2 orders higher, but they did not become very viable because what happened was that high gauge factor semiconductor gauges have lost viability because of much less expensive amplifiers which have taken their place. Therefore, with comparatively lower strain gauge based setups, but with amplifiers down the line, more economically viable electronic measurement systems have gained more popularity. Conventional metallic strain gauges are generally of 4 types based on Constantan, Karma, isoelastic and platinum tungsten. Let us see some more details regarding them. What is Constantan? It is a copper nickel alloy with gauge factor 2, widely used in transducer gauges. It has exceptional linearity over wide strain range, which means if you plot the strain versus the voltage output, then you will have a nice straight line for a wide range of strains. That is what we mean by linearity. And it is easy to manufacture, easy for soldering when you try to fix it on surfaces, but when exposed to higher temperatures of the order of 70-80 degrees or more, then the resistance of the strain gauge starts drifting, and it increases exponentially with temperature, and therefore, it is not at all recommendable for high temperature applications. So, that is the limitation. What about Karma? It is a nickel chromium alloy with slightly better gauge factor, good linearity like Constantan, and it has good resistive stability at high temperature. Therefore, this is certainly a better choice for high temperature applications. Isoelastic alloy gives very good fatigue life, and therefore, wherever you have to make dynamic measurements, that means there is change in the loading of the model, there is a rapid fluctuation in the loading, therefore, rapid deformation of the strain gauge as well, then isoelastic alloy could be a good choice. It has a superior gauge factor, almost 50% higher than Constantan and Karma, but it has poor zero stability with temperature variation. So, when temperature varies, the zero setting can become unstable. Platinum tungsten alloys like isoelastic are used in dynamic measurements. Its gauge factor is almost twice that of Constantan and carbon. So, that was a brief discussion on the different alternatives. Now, very often these resistances are arranged in the Wheatstone bridge formation. So, let us briefly recall about Wheatstone bridge circuits, which you must have learnt much earlier in your +2 courses and even in your other courses in engineering on electrical technology. So, here is a practical application in the aerodynamics world. So, when there is a change in resistance in the strain gauges due to the applied load, you can convert them into a change in voltage, and that voltage change is basically going to come from a Wheatstone bridge circuit. So, we have been talking about an output voltage coming from the transducer, but where is it coming from? It is essentially coming from a Wheatstone bridge circuit. We mainly use 2 kinds of circuits, summing and differencing kinds. When we look at applications in wind tunnel balances, the differencing kind is used for measurement of force, while the summing kind of circuit is for measurement of moments. We will learn more about them in upcoming lectures, but let us have a quick look at the circuit for a summing case. We will make a small sketch of a summing circuit. So, let us first put the resistances together. We will take 4 resistances R1, R2, R3 and R4. We will give an excitation voltage and there will be a consequent output that will be produced by the bridge. So, this is the excitation that we are providing, let us say V. Take note that the R1 resistor, which is one of the strain gauges in the Wheatstone bridge, is under compression, so is R2 and they are opposite to each other. R3 is in tension, so is R4. This forms the pattern in a summing circuit. Now, why it is called as summing circuit and another one which we will see soon is called as a differencing circuit will become clearer when we do the calculations in another lecture, but for now let us get used to the arrangement first, how we arrange the resistors and which one is under compression and which one is in tension. So, what we get as an output from the bridge is an output voltage, we will mark it as delta V, which is way smaller than the excitation voltage. And often needs to be amplified before we can suitably use it for our data processing. So, here you note that the opposite resistances are in compression or tension, and note that R1 and R2 they are in compression, R3 and R4 are in tension. So, keeping this setup in mind will be very useful. We looked at the summing circuit, let us move on to the differencing circuit. We are already familiar how to draw the Wheatstone bridge. You will notice that this time we will just rearrange the resistances. There is no other change essentially in the circuit. How do we rearrange them this time? Keep comparing with what you saw for the summing circuit and now see what we are changing over here. Then the change will become apparent to you. So, you see in the previous one R1 and R2 were opposite to each other. Now, they have come adjacent to each other. They are still under compression. R3, R4 they are still under tension like they were in the previous case, but their locations have been changed. That is the main difference that you notice over here. Now, let me use some other color so that you can more easily see. So, this is the excitation that you are providing, this is the voltage input. Which we also called as the excitation, and what you finally need as output from the transducer that comes on the other side. So, this is where you will get the voltage output. You will have the amplifier here, from where we are showing a meter. So, this is essentially the configuration for differencing circuit. As I said already that we are going to look at these configurations in more detail in the upcoming lectures, where we will also understand the significance, why we call them as summing and differencing. So, let us try to recapitulate what we learnt in this lecture. We discussed about basics of electronic transducers and their importance in wind tunnel instrumentation. Variable resistance transducers were discussed in detail. Gauge factor and its dependence on Poisson's ratio was shown. The concept of Wheatstone bridge circuit was discussed, and two types of circuits, namely summing and differencing circuit, which are used for force and moment measurement in wind tunnel balances, was introduced. Thank you.